In this video, we're going to look at the magnetic field around a wire, around two wires, and then around multiple wires. So the very fundamental idea of this topic is that moving charges create a magnetic field. Right, this is a fundamental law of physics, and when this was discovered, this unified electricity and magnetism. So obviously this is part of the topic that is electromagnetism, and now we're really starting to understand why we're looking at electromagnetism. It's electricity and it's magnetism. They are the same thing. There's only actually four forces in physics. There's electromagnetism, there's a strong force, the weak force, and there is gravity. Okay, only two of those we care about at GCSE. The strong force and the weak force are to do with the inside of the atom, the nucleus, and they are something we look at A level. So what do students need to know? Actually, before that, what we should make a link with here is we should say, well, moving charges create a magnetic field, and then we should make a link back with electricity, where we say current is the rate of flow of charge, all right? Because moving charges is a current. So we can also say that currents create electricity. Sorry, currents create a magnetic field. Okay, this is the fundamentals that students need to know. So the first thing we're going to look at is a single wire. So this is where it gets a bit harder, okay, because what we're asking students to do is to be able to visualize 3 dimensions, right, when we're looking at a 2D surface. And that's quite hard for students. It's quite hard for adults as well to do a lot of the time. So there's loads of demos we can do. Right, everything I'm talking about can be done as a demo really easily. All you need to do is you need to get a wire, and you need to get a power supply and some plotting compasses, or you can get a strip of foil, a couple of crocodile clips, and the same thing. All right. So if we look at a single wire with a current going through it, the magnetic field that's created around it is actually a circular magnetic field. So this is how it's typically drawn. But this is actually a 3-dimensional picture that we're doing in representing in 2 dimensions. So the field is actually perpendicular to the wire. So this is important, of course, because this is its true direction. So what you have to imagine is the wire is maybe coming out of the page, all right? And if the wire is coming out of the page like this, then the field is around it like this. Okay, so it might be useful to do this. If you do it as a demonstration, you can obviously get this piece of wire. You can clamp it vertically between 2 clamps, and then you can get yourself a piece of cardboard, and you can put the cardboard, you can make a small hole in the cardboard, put it around the wire, and then you can use lots of plotting compasses around the wire, and you'll see that the plotting compasses all point in this circular direction. All right, so this is really a must do as a demonstration. There are some videos of this as well, but it's really easy to set up. Now, if you're trying to demonstrate something like this, like my very messy diagram where wires coming into or out of the page, and you want to represent that on a piece of paper, you need to use this convention. You need to use this symbol here, means out of the page, and you need to use this symbol here, means into the page. Now, the reason these symbols are chosen, or one way to help remember them, is if you think of it as like an arrow. Okay, if it's coming towards you, you're going to see the tip, you're going to see the arrow like this, and if it's going away from you, you're going to see the feathers, so you're going to see this. So if I'm coming out of the page here, I might draw it like this, if I draw something going into the page. How do you remember which direction the arrows go, the magnetic field goes? Well, you need to use the right-hand grip rule. And this is really simple. You get your hand and you make a shape like this. And then your thumb is the direction that the current is going. And your fingers is the direction that the magnetic field is going. So when you hold it like this, obviously your thumb is perpendicular and your fingers go around in a circle. It's right. It's quite a good idea to get students actually write on their hands because it does help them remember. So this is the most basic idea, and then we can extend this. We can say, what if we have two wires? So this amazingly used to be on the A-level syllabus, and then it was brought down with the changes to the GCSE, and it is really quite tricky, this. So again, this can be demonstrated really nicely. You just get two wires, you clamp them, and you put a piece of cardboard around both of them with two holes in, and again you put some plotting compasses at various points, and then you will see the shape of the field. You can also do it with iron filings and just giving it a light tap, but they don't tend to work quite as well because the field tends to be quite weak. You'll probably also notice when you do this and wire it up that it trips quite easily. The fuse pops out, right? Because the wires obviously have a very low resistance, and you need a relatively high current going through them in order to notice the field. So when you have two wires, we have two possible scenarios. We can have scenario one, where the currents are going in the same direction, and scenario two, where the currents are going in opposite directions here. And students need to be aware of both of these. So when they are going in the same direction here, what the field does is it actually ends up doing this. So again, again, the direction can be found from this. So let's explain this. If we think about one wire, we're going to get this field here. If we get a second wire next to it, so let's just draw a second wire over here next to it, its individual field is going to look like this here. Again, from this right-hand rule. So when we bring them a bit closer together, these fields are going to interact, right? And magnetic fields are vector fields, as we discussed in a previous video. So what this means is, with vectors, we can add them together. And it is worth explaining this to students, because I think it does help their understanding a little bit, and I think it does then start to tie concepts together. So we can add them together, or we can subtract them. And if you want to make a nice link with maths, right, they'll have probably seen things like this in math, or they would have seen things like this in GCSE forces anyway. If you have two vectors, two instructions, you add them together, the resultant looks like this, for example. Or if you had two vectors like this, right, this is like a year 7 forces thing. We just don't always use this language, right? What's the resultant? Well, we subtract them, and the resultant is this. We can do exactly the same with magnetic fields here. So if we think about these fields here, we have two arrows both pointing left. So that's like as saying we've got two forces both pointing left. What's the resultant going to be? The resultant is going to be this big force here. So it'd be this arrow. This arrow and this arrow, they're both pointing left. We add them together, we get this. So this is our resultant force, or our resultant field. Now, because of the pattern of this field, what actually happens between these two wires is there is actually a force of attraction. And students should know this, and we should probably demonstrate this as well. This can be demonstrated nicely with strips of foil. It doesn't really work so much with wires, because the wires are quite heavy and you don't really notice them move. But if you replace these with two vertical strips of foil, and again you put some crocodile clips on the end, and then you connect it all to a power supply, you will notice the strips of foil move together, and it's a very nice demonstration of attraction. When we have two wires with the current going in opposite direction, okay, we have a scenario like this. So I'm going to draw the individual fields, and we can think about what's going to happen. So the individual fields, again, from this right-hand grip rule. Now the arrows are going to be going in opposite directions this time. So because they're vector fields, because they add and subtract, right, this is like this example here, where they're going in opposite directions, and so they're going to oppose each other. So what the resultant field actually ends up looking like is this. Now, this is actually a pretty messy diagram, but this is the basic idea. What you will find is the fields oppose each other, and they then end up with this kind of pattern here. And because the fields are opposing each other, because we've got arrows pointing towards each other, they don't add up like this, and therefore they don't attract. We will actually see a force of repulsion between the two of them. So if we really want to think about simplifying this, arrows pointing towards each other from the right-hand grip rule means that the fields oppose each other. If they oppose each other, they repel. Fields are in the same direction here. They're going to add up together. If they add up in the same direction, they're going to be attracted to each other. But you will need a neater diagram than this one. And again, this can be demonstrated with strips of foil, and you very, very nicely see that with strips of foil, they will oppose each other, they will repel each other, and they will end up looking like this. The very last place we're going to go with this is we're going to think, what if we had lots and lots and lots of wires all like this with the currents in opposite directions to all of them? What we're actually now creating is a solenoid, right, a coil of wire. And we looked at this when we looked at electromagnets and uses of electromagnets. So with a solenoid, let's put the current going in this direction here. What do we have? We have individual bits of wire here in the loop where the current is doing this. So if you imagine doing this for every single wire here, all the ones next to each other, what you end up with is you end up with this field that looks like this. And you will notice this looks a lot like a standard bar magnet, okay? And how do we work out which direction the arrows go in? Again, we use this right-hand grip rule, and we put our fingers the direction the current's going. So the current's going this way here. So our fingers are going to go this way, and then our thumb is going to point the direction of the arrows, and therefore we've got our north and south pole. So that's pretty much it. Students need to be able to identify these. They need to be able to recognize these as a practical, a setup, either with foil or with wires. And they need to be able to think about what happens in terms of the field, in terms of this right-hand grip rule.